lecture I am going to take you back a little bit in this course. We had discussed the intermediate axis theorem in one of the previous lectures when we discussed the stability of rotating bodies, spinning bodies and unsymmetric bodies. And then we had discussed how the intermediate axis or the axis which has intermediate moment of inertia value is unstable. If you start spinning with that axis, along that axis, then the body has instability. We are going to look at this theorem in a little more detail. We are going to look at the stability of rotating rigid bodies and understanding the dynamics in terms of what are known as Poinsot construction. Then I will show you how to visualize the rotation of a rigid body, and very interesting effect we are going to see, the Dzhanibekov effect, which was observed by a Russian cosmonaut in space. Recall, we had discussed this Euler's equation. Whenever we discuss rigid bodies, unsymmetric rigid bodies, we consider this body fixed frame. Here I have shown this x, y, z as the body fixed frame of an unsymmetric body, and I have considered this ordering, I x x is less than I y y is less than I z z. We have the Euler's equation written in body fixed frame in the principal, and this frame is the principal body fixed frame. Therefore, we have this Euler's equation in very simple form. Recall the situation when the spin state is such that omega y, this is the intermediate axis, I y y lies between I x x and I z z. I give a spin in the y axis direction. I want to study the stability of this. When we want to study the stability of this spin state for this unsymmetric body, what we do is we perturb the actual angular velocity, we perturb and we see what happens to this angular velocity vector. How does it evolve? How do the perturbations evolve? This is how linear stability is done. So, we are studying the linear stability of this system about the intermediate axis, the spin about intermediate axis. We have seen in our previous discussion what happens when you give spin about the lowest angular moment of inertia direction and the highest angular moment of inertia axis. They are both stable, but just to recall this intermediate axis theorem, let us look at the perturbations on this basic spin state where I give spin about the intermediate axis. Here I will assume that these perturbations are small, epsilon x, epsilon y, epsilon z. They are small, so that I can neglect product of these small quantities. Now, if you do that, the first equation, for example, this will be I x x omega x dot will give me epsilon x dot, whereas from here omega y is this times omega z. Now, you will get a product epsilon y epsilon z, and that has been dropped, only sigma and epsilon z product has been retained. Here we are going to drop both, because this will be epsilon x epsilon z, therefore, they get dropped. And similarly, the third equation, these things we have discussed before. We can recast these three equations. What it tells us, this equation tells us is that the epsilon y is not going to change, the perturbation on in the spin direction is not going to change in the first order. Here and the other two equations are coupled. What I can do is I can take a one more derivative of the first equation and use epsilon z dot from the third equation here to get a self standing equation in epsilon x. Similarly, I can do for the third equation. The sigma p square which is given by this, is a positive quantity. Why? Because I z z is the highest, I z z minus I y y is positive, I y y minus I x x is also positive, these are positive. Therefore, this is a positive quantity, but we have this additional negative sign, and if you look at the solutions of these equations, they are of the form some constant exponential omega p t plus another constant exponential minus omega p t, where omega p is obtained from here, and this is in terms of the spin that has been given to the body. You will note that we have an exponentially diverging term. Therefore, this perturbation, and so also the perturbation in z, the perturbation in x and perturbation in z, these two perturbations will diverge. There is a divergence instability. This in linear analysis we would say it is an unbounded solution, but really it will not be unbounded, because we are doing linear analysis, and as the values increase, this this simplification itself is not valid. Therefore, linear analysis can only be used to say that the system is unstable. This spin state about the intermediate axis is unstable. This was the crux of the matter or the statement of intermediate axis theorem. The spin of a body with unequal principal moments of inertia about the intermediate moment of inertia axis is unstable. So, for an unsymmetric body, if you give a spin about the intermediate axis in terms of the moments of inertia, principal moments of inertia, then it is unstable. That spin is unstable. But what is the meaning of instability? What is unstable? What will happen to the body? That we are unable to say from this linear analysis. Linear analysis will not tell us what will happen. It only tells us that it is going to move out, the perturbations are going to grow, but it never tells us what happens. That is what we are going to look at. Now, this theorem was known since 1834. Louis Poinsot, in his book, he studied rotation of bodies and he proposed this theorem. Later on, in 1985, experiments in space they revealed that this motion of the body shows very interesting properties. I mean, it shows a very interesting behavior in terms of this spin or its motion. When you give spin to a body with unequal principal moments of inertia, and this was observed in space by Dzhanibekov, Russian cosmonaut, Vladimir Dzhanibekov, and this effect is named after him, Dzhanibekov effect. And what is this effect? We are going to see in a moment. But the result was known, this instability and what happens was known to Louis Poinsot, but it was not observed. It was observed in a space experiment. How do we visualize this rotation? Because our linear stability analysis did not give us any visualization, any clue how the body will behave when you give a spin about the intermediate axis. Poinsot devised an interesting way of looking at it. We start with this consideration that our body is under no external force, no external torque or moment, therefore, it is force and torque free motion, and therefore, energy has to be conserved and angular momentum has to be conserved. What is conservation of angular momentum? Remember, energy is a scalar quantity. So, its conservation means its value is going to remain the same throughout the motion. The value of the total mechanical energy, which here is only the kinetic energy, rotational kinetic energy, that is going to remain constant. The value is going to remain constant. What is the meaning of angular momentum being conserved? It means that its magnitude as well as its direction both are invariant, they will remain the same. In other words, if I give a spin about the x axis, angular momentum conservation means it is going to whatever happens, I mean unless we have we are having torque free and force free motion, therefore, however it precesses or its angular momentum is going to point in this direction only, absolute space, this direction, because the frame is body fixed. Remember, frame is body fixed, frame can reorient itself. But the angular momentum vector is going to remain same in the same direction as seen by an inertial observer, that is not going to change, which means that the angular momentum will have varying projections in the 3 directions, and this is key to this visualization. Angular momentum vector will maintain its direction and magnitude in inertial space. The frame which is fixed to the body, that can precess, that can do whatever it likes, but angular momentum, the total angular momentum of this body is going to have the same magnitude, same direction. Therefore, its projection in these 3 body fixed frame axes will be changing. It will change, but it will be periodically, if it is precessing, it will periodically change, of course. Okay, with that understanding, let us write down the energy and angular momentum. Energy is half omega dot I g omega, we know everything. The moment of inertia tensor is diagonal, because we are considering this frame as the principal body fixed frame, and omega x, omega y, omega z are the 3 components of the angular velocity. This is the energy, and this is going to be a constant quantity, constant scalar. Angular momentum, which is given by the moment of inertia tensor times the angular velocity, it is a vector quantity I 1 omega x I cap, I 2 omega y j cap, I plus I 3 omega z k cap. Now, magnitude wise and direction wise this is going to remain same, but handling a vector quantity like this and understanding this vector quantity may be slightly more complicated. So, what was done by Poinsot is that you consider the magnitude square of the angular momentum, that is a scalar quantity, and that is also going to remain constant, but we are now losing track of the direction, but in the back of our mind we must always remember that the direction is going to remain fixed, and that we are going to see soon what it means, the direction remains fixed. But with this new consideration of the square of the angular momentum, which is a scalar, and the conservation of energy. Now, we have 2 scalars, this is the first scalar, this is the second scalar, and both have to be constant. The direction thing will come a little later. Now, we have this energy and angular momentum magnitude square. We make a redefinition. We make this redefinition to kind of simplify the representation of these constants in terms of some familiar geometric objects. Here I have used lowercase h x, lowercase h y, lowercase h z, which are I 1 omega x by a constant quantity in terms of energy, energy is a constant, I 2 omega y by that constant, I 3 omega z by that same constant, and you will notice this new vector lowercase h vector is equal to the angular momentum vector divided by a constant quantity 2 times under root 2 times the energy. Therefore, I can write this, that the lowercase h vector is proportional to, by proportionality, proportional to the angular momentum vector. By proportionality I mean, and what is very important now is that it will have the same direction as the angular momentum vector. This lowercase h vector will have the same direction as the angular momentum vector, but its magnitude is the scaled magnitude of the angular momentum. Therefore, this h vector will maintain its magnitude, it is a scaled magnitude of the lowercase h vector, will also have a constant magnitude, because it is being divided by under root 2 e, which is a constant, and h is definitely a constant. With this redefinition, you can write the kinetic energy, you can rewrite the kinetic energy expression in this form. And this is a very familiar geometric object. It is an ellipsoid with its semi axis as under root I 1, under root I 2 and under root I 3. They are the semi axis, where remember I 1 is the smallest, I 3 is the largest and I 2 is intermediate. Therefore, we have an ellipsoid which represents the energy condition, energy conservation constraint. And the angular momentum magnitude conservation constraint, h square being constant, that boils down to this expression, h x square plus h y square plus h z square is equals to h square by 2 e. What is this? This is nothing but a sphere, and this therefore represents the angular momentum conservation constraint. Therefore, we have the energy conservation constraint and angular momentum conservation constraint as an ellipsoid and a sphere. We have the kinetic energy here, I mean there is no potential energy contribution, but is the total energy is the kinetic energy only. Therefore, energy ellipsoid and angular momentum sphere. And note the ordering of the principal moments of inertia. Now, this lowercase h x, h y, h z appear in both these two conservation equations, and to I mean these values will be identical, and so they must satisfy these two geometric conditions, and must therefore, so the same values must satisfy both the same values of lowercase h x, h y, h z must satisfy both the things. In other words, acceptable values of lowercase h x, h y, h z must come from the intersection of these two geometric objects. Otherwise, these h x, h y, h z values will be different. If they are not from the intersection, they are different values. Both of them must be satisfied by the same h x, h y, h z. Therefore, they must come from the intersection of the ellipsoid and the sphere. So, valid values of h x, h y, h z, the lowercase ones, they must satisfy both equations, and therefore, they must lie on both these surfaces, or in other words, they must be at the intersection, they come from the intersection. And how can a sphere and an ellipsoid intersect? Under what conditions? The radius of the sphere must be greater than the lowest semi axis and smaller than the largest semi axis. Only then intersection is possible. If the radius of sphere lies outside this region, then either the sphere will enclose the whole ellipsoid, or the ellipsoid will enclose the whole sphere. There will not be an intersection, and then there are no valid values of h x, h y, h z. Let us consider the first case where we are giving a spin about the lowest moment of inertia axis, which is the x axis. I have shown in the figure. This spin is being given about the x axis, and there is a perturbation on the spin in the other two directions, y and z. If there has to be an intersection, then this must be the condition satisfied by the radius of the sphere. This is the radius of the sphere. You see, this is the radius square. So, this is the radius of the sphere. Radius of the sphere must be greater than the lowest semi axis and the intermediate semi axis. In that case, I have this intersection. Now, therefore, all these values on this curve, this is a closed curve, there will be a closed intersection curve, all these values are valid values. And when I give spin to the lowest moment of inertia axis, we have seen this before, that there is a precession of the body. And how will these so how will the body precess? Let us understand that. Remember that the moment of inertia is in this direction. Our lowercase h vector and the angular momentum vector, they are roughly pointing in this direction. These are small quantities. These are small quantities. Roughly the moment of the angular momentum points in this direction to begin with at the very start. But now it says that h values must come from this intersection. In other words, if I consider some frame like this, some inertial frame, then h must have these magnitudes and these directions, but actual h cannot change direction. Actual h cannot change direction. So, what is happening? For let me take this point. Let me take this point. The h vector is something like this. It has projections in now z direction, in this vertical direction, in the inertial direction. What does it mean? How can this happen? This can happen only when the frame is oriented towards like this. Frame is oriented so that this has a projection in this direction. Only then this can happen. Only then this can happen. In other words, the frame must reorient itself. The frame reorients itself to get this projection along the z, and hence as you see this is moving on this closed curve, the h vector is moving on this closed curve, but actual direction is not changing. Therefore, the body is actually precessing, so that there is projection in the other directions, in the z and x directions. So, the body is precessing, body has to change, because if the frame rotates and the body is fixed to the frame or frame is fixed to the body, then the body also changes its orientation, and that is how we can understand how the body will actually precess. Let us move to the next case, where I have given the dominant spin in the intermediate axis. There are some perturbations of rotation in the other two axis directions. And if you now draw that energy ellipsoid and the angular momentum sphere and their intersection, this I have drawn for this very special or very special value of the radius of the sphere, which is close to the intermediate semi axis. In that case, the intersection is like this. It's on, there are two curves, this is one curve and this is the other curve, they are intersecting at this point. If I give slightly lower energy, which means the radius increases, it will go to this blue curve. I mean the motion will go to, the intersection will go on this blue curve. Otherwise, the motion will be, if the radius is roughly this much, then the intersection will be along these two curves. And this indicates that Now, h x h y, that lowercase h x h y h z, that will have values on this curve, and this is connected to the antipodal point. Antipodal point is the point which is diametrically opposite on the sphere. Now, if h x, h y, h z are to change values like this, but its direction actually, remember the angular momentum is of this direction. If it is to have projections, other projections in x and y, the frames themselves will have to rotate, the frame vectors will have to rotate. In other words, the frame has to rotate, so that this vector has projections in other directions. The frame may look like this, for example. In that case, h vector will have projections in x and z directions. And since frame has to reorient, it means the body also will reorient. Now, what is the meaning of this point going to its antipodal counterpart? It means the body will completely flip. This y axis now is in this direction. After some time, the y axis will point in this direction. Only then it can go to the antipodal point, because the angular momentum or this h vector is in this direction only. It cannot, that will not change, that is an invariant quantity. Therefore, the frame has to flip, it has to go, the y axis has to go to the other side. If you give similarly omega, the dominant spin in the z axis, this is what you will observe. The intersection will now be this, and the radius restriction will be between, it should lie between the intermediate semi axis value and the largest semi axis value. So, that is the restriction on the radius, and the intersection will be on this curve, again this closed curve, but it remains, the h x, h y, h z values will remain close to this vertical axis. In other words, the body is going to precess something like this, it is going to precess, so that the angular momentum or the h vector, lowercase h vector, is always in that same direction, but its projection is changing. That is why the h x, h y, h z lowercase values are changing like this. And you can also tell which way it is going to precess. We have studied this, we have studied two kinds of precession, prograde or direct precession and retrograde precession. Retrograde precession takes place for oblate like bodies, when the bodies are oblate, and this is close to that. Therefore, the precession is going to be retrograde. In other words, if this is the spin direction, then the precession will be in this direction. It is going to precess like this. Now, various interesting things happen if the body is slightly flexible. We have been discussing about rigid bodies, but let us imagine that this body is slightly flexible, and in many cases this has happened, that slight flexibility of the body leads to dissipation of energy. Why? Because every physical body, every real world body has first of all little flexibility, and any flexible body will have internal dissipation. And when energy dissipates, which means that E is going to reduce slowly, very slowly, because the flexibility maybe is very low and the internal dissipation is very low. So, this energy, kinetic energy of the body will slowly damp out. If it damps out, what is going to happen to the radius of the sphere? Radius of the sphere is going to increase. When energy goes down, the radius is going to increase. And what is going to happen if radius increases? You can see from here, if wherever we start from, if the radius starts increasing, eventually it is going to come to this kind of thing, and finally the sphere is, this is the final state where the sphere is going to be tangential to the ellipsoid. The ellipsoid will be completely inside the sphere except for these two points where it will touch, and roughly. So, that is going to happen, and therefore, this body is going to eventually, wherever you start from, whichever spin you give, if there is little bit of internal dissipation and flexibility and internal dissipation, eventually the sphere is going to grow and going to be in this kind of a state, this kind of precession state. This reduction of energy, but conservation of H. H is conserved because there is no external torque or force. There is no external torque or force, therefore, angular momentum will be conserved, but energy is going to reduce, and therefore, this radius is going to finally tend to under root I 3. It will go very close to under root I 3. This is known as the major axis theorem. The spin finally will move very close to the major axis in terms of the moment of inertia. So, this is what is going to happen. I 3, it is going to move to the z axis, the spin is going to eventually move to the z axis. This has happened in the case of Earth, because it spins about the maximum moment of inertia axis. It has also led to some very strange occurrences in satellites, where a satellite was given a spin about its minimum moment of inertia axis, a satellite which looked like this slender bar, circular bar. It was given a spin about its minimum moment of inertia axis, which is this axis of symmetry, but because of there were some flexible antennae which dissipated some energy, kinetic energy, finally it started moving, spinning about its maximum moment of inertia axis. This has happened in satellites. Now, we visualize this rotation, whatever we have discussed. We use the generalized coordinates psi, theta, phi, which are the yaw, pitch and roll coordinates. We can write down the Lagrangian. This we have discussed. In free space there is no potential energy, therefore, we have only the kinetic energy. Lagrangian is the kinetic energy, and I write the kinetic energy in terms of the yaw rate, pitch rate and roll rate, and of course, this moment of inertia tensor is completely diagonal, because this xyz frame is principal body fixed frame with this ordering. Now, the angular velocity is parameterized by this yaw, pitch, roll coordinates in the body fixed frame x y z. This we have discussed in a previous lecture. You recall the transformation from the body fixed frame, this is a frame 3, to the inertial frame 0 using the fundamental rotations about z0 by an angle psi, which is the yaw angle, about the new y, which is y1 by an angle theta, rotation about y1 by an angle theta, which is the pitch, this is shown in the figure, and about the new x axis, which is x2 axis, a rotation by an angle phi, which is the roll. And we had calculated this rotation matrix from 3 to 0. Also recall, we discussed this representation of the angular velocity in this body fixed frame. It is the yaw rate times z naught represented in the third frame, theta dot, which is the pitching rate about y1 represented in the third frame, and the roll rate about x2 represented in the third frame. All these things were discussed previously, and we had this transformation from the yaw, pitch, roll rate vector capital psi dot to the angular velocity vector, and this is the transformation, this is the details of the transformation. This we had discussed. Now, we write down the Lagrangian using the moment of inertia tensor and this representation of omega. in terms of the roll rate, yaw rate, pitch rate, etc. This is the Lagrangian. And the equations of motion can be very easily obtained by using the Lagrange's equation of motion. The generalized coordinates are psi, theta and phi. You have 3 equations of motion. For the initial velocity, because what I am going to do is I am going to solve these equations of motion numerically, because otherwise they are highly nonlinear and coupled. We cannot solve them analytically, we will solve them numerically. To set the initial conditions on the yaw rate, pitch rate and roll rate, I use this transformation, it is inverse of the transformation really. I give some initial angular velocity to the body at time t equal to 0, and correspondingly I find out psi dot, theta dot and phi dot at t equal to 0, and I start with some value of psi, theta, phi. I have considered the principal moments of inertia hypothetically 1 kg meter square, I2 is 2 kg meter square and I3 is 3 kg meter square. I start with spin about the minimum moment of inertia axis, which is the x axis, and I have written down what is the omega at t equal to 0. From here I can very easily find out using the transformation inverse what are psi dot, theta dot, phi dot. And if I do that, I have plotted, I have animated this, I have solved these equations of motion and drawn the frames according to that the values of yaw angle, pitch angle and roll angle. I have calculated the frames and I have just plotted that as a function of time. And you can see that the Poinsot construction, the intersection of the sphere, the angular momentum sphere and the energy ellipsoid is like this, and here the precession, if you note the precession, it is direct precession, the angular velocity is this, and to change values of the lowercase hx, hy, hz, the frame has to reorient, and this is direct precession. If I now give a spin about the intermediate moment of inertia axis, which is the y axis, let us see what happens. And here I have drawn the Poinsot construction. Now you will see that y axis suddenly goes and orients at the antipodal point. Why? Because the point must move, and the hx, hy, hz values must move on this intersection line and go to the other side. And how is this possible? Because h cannot change its direction, therefore the frame must change direction. And this is a very interesting behavior. You can always see that this is the direction of the angular momentum. When it goes to the other side also, the spin is this way. When this comes back again, you will again notice that the spin is counterclockwise as seen from the front. See, the whole body is rotating, spinning in the counterclockwise direction, whether the y axis points this way or that way. Therefore, the angular momentum actually is conserved, and the frame changes its orientation to take care of the change in values of hx, hy, hz. Here I show the Dzhanibekov effect. This video of course comes from NASA. This is shot in the International Space Station, and you can notice what is happening to the T-shaped object as it is spun, and the corresponding video, corresponding animation also can be run along with that. Of course, the animation is running slowly, not in real time. This is known as the Dzhanibekov effect, observed by Vladimir Dzhanibekov in space. but this observation is a little difficult to repeat on earth. You can do it by high speed photography, but otherwise continuous motion as possible in space is not possible on the earth. It is a little difficult. So, let me summarize what we have discussed. We have studied the stability of rotating bodies. Using the Poinsot construction, we have visualized rotation or the growth of these perturbations, because our linear stability analysis, remember, did not give us, other than saying that the system is unstable at the intermediate axis spin, it did not give us any visualization of what will happen. Poinsot construction gives us. We have visualized the rotation of rigid body, and we have also looked at the major axis theorem, which happens for flexible bodies with internal damping. Finally, I have shown you the Dzhanibekov effect, which is observed in space, and with the simulation it replicates that effect. With that, I will close this lecture.